All right, so we've just gone over the exam papers. You have a homework assignment due next Wednesday. I'm not giving you any rest, not much anyway. So we're going to go over a couple of examples in today's class that will allow you to get started on homework 7. It's available on Blackboard right now. It's a couple of problems from the book and then something that you're going to use in the project. I'm asking you to digitize a curve just to get an early start on the project. And speaking of the project, the first part of that that's on your plate is the demand estimation. So demand estimation needs to be uploaded before class on Monday, the 9th of March. So what we're going to do now is move into Chapter 10 in the book, and Chapter 10 is dealing with open channel flow. Except for the project, we're done for now with pipe flow. So closed conduit flow is the first part of the semester. Let me jump through that for a second. So here is what we've done thus far. The first part of the course has to do with flow through a pipe, and if we're going to distill it down to a single question, the question might be, what's the pressure in the pipe, accounting for friction losses, accounting for a pump, accounting for elevation differences. That's probably the most common thing that we're modeling, is understanding how the pressure changes as water flows through a pipe. If we're going to distill the next part of the course down into a single question, for the rest of the semester, what we're going to be looking at is how deep is the flow depth for certain conditions. If we have an open channel, meaning a river or a stream or a creek or a canal, if we're sending a flow through that, how deep is the water going to be? That's what we're going to be looking at. Lots of different considerations and methods for predicting the flow depth. So the closed conduit is the first part of the course. Open channel flow is the second part of the course. Now if I just jump back quickly, for the design project, remember I already mentioned that part of it is going to be demand estimation, trying to figure out how much water do they need at each of these green arrows. But the part that's on the homework is looking at this figure in a little bit more detail. And in the homework problem I say, let's say for instance that in a certain town we know that their peak demand is 560 liters per second. So on the maximum day of the year, the highest flow rate that's going to be demanded from this particular town is 560 liters per second. In the homework assignment, I ask you to predict on an hour-by-hour basis what's the flow rate for that town by using this curve. So you notice here on the vertical axis, it's a number that you could scale based on this being a flow rate of 560. So 560, it looks like, corresponds to a percent of 275% of the average day. So if you wanted to know what is the average daily flow, if 560 is 275% of the average day, then you can find the average day just by dividing by 275. But you can do more than that, because you could digitize this curve, and so like for example 100 divided by 275 multiplied by the flow rate, that'll tell you the flow at 12 a.m. Or if you want to know the flow at 6 a.m. So the flow at 6 a.m. is going to be 150 divided by 275 multiplied by 560. So in other words, by following this curve and then using the units on this vertical axis, it's a linear unit scale, then as long as you know the flow rate at the peak, then you can find the flow rate through the entire day. And this is a temporal distribution, which is just describing the variability over time. So that's on the homework. It's going to be due on Wednesday, so if it's not making sense after you read through the problem description, then come see me and I'll show you what the answer kind of looks like, the form of it. But I hope it'll be as simple as digitizing this curve and then setting it up in Excel. Excel makes it easy to solve a problem like this. If you have hour in one column, percent in the next column, then you can very easily calculate the flow rate based on the percent. Okay. So it's not just hydraulics that we're learning this semester. The whole point of this design project is partly to reinforce what you're learning in hydraulics, but it's also to give you something you can put on your resume, that you know how to use a design software. Knowing that you're capable of actually doing meaningful real-world work in water gems is going to be something that employers might be interested to know. And so, like, this course overall is partly about the hydraulics, but it's also teaching yourself to learn. And I try to introduce as many examples as we have time for during the semester, but occasionally there are going to be things that you just have to figure out on your own. And especially once you graduate and start working, you'll learn really quickly, like I learned really quickly, that your boss is very different from your professor. Like, the professor is always eager to answer questions and, you know, anxious to help you learn, but your boss just wants you to do your work. He doesn't want you to show you how to do your work. And so in a lot of cases, it's a rude awakening when you get on the job and you just have to figure out how to do it yourself. So you're maybe looking at old designs, or reading through design manuals, or looking up tutorials in a help file for software. So teaching yourself to learn is good practice. You know, part of what we're doing this semester is, I hope, teaching you the habit of breaking a project into more manageable pieces instead of trying to just do it all at the last minute in one big go. Trying to think of what the discrete elements are of a project and getting practice with the time management. The idea of iterative design and optimization is an important part of what I hope you'll learn this semester, as well as learning how to apply that water gem software and being able to, you know, walk away from your time at Marshall with a software package that is known and accepted throughout the industry as being like the most powerful hydraulic analysis tool available for municipal design networks. And then the other thing that you definitely are picking up, not just in this class, but in all of your engineering classes, I'm sure, is determination and grit and the willingness to just keep going and get through things that are difficult. And you know, engineers have a really hard go of it, but then when you graduate, you have much more employability than some of the easier majors. And I don't know if many of you heard me tell the story before of when I was in college. My apartment looked out over a swimming pool and a hot tub, and I'd be sitting there working on my concrete homework, and the English majors would be having a good time in the pool, and then I'd be working on my steel assignment, and then I'd notice the philosophy majors were in the hot tub, and I never got into that pool the whole time I lived in that apartment. But then on graduation day, although I had a miserable time while I was in school, you know, later on it pays dividends. And so you're going through the ringer right now, and it feels like such a high-pressure environment, but you'll be employable when the economy gets bad. You'll be employable when the economy is good. The American infrastructure is in such bad shape that you graduating civil engineers are going to have plenty of work to do for the entirety of your career. There's just so much money flooding into civil engineering projects right now that it's really kind of nuts. So all of that kind of overview stuff aside, let's talk a little bit more about flow types. And you probably remember back in fluid mechanics that we classified flow into different categories. There was uniform versus non-uniform flow. And what you'll remember, I hope, is that what causes non-uniform flow is convective acceleration. Convective acceleration is the acceleration that velocity changes as a function of position. And it could either be the magnitude of the velocity or the direction of the velocity that we're talking about in convective acceleration. So that's one way to classify flow, is uniform versus non-uniform. And in open channels, we'll very often have non-uniform flow. It's only in an engineered channel that we'll see uniform flow. But in nature, if we're talking about a creek or a river, it's going to be non-uniform because those types of channels are pretty irregular. Another way that we broke the flow up into categories was steady versus unsteady. And remember, this has to do with changes over time, so the temporal distribution. And the type of acceleration that causes unsteady flow is local acceleration, which is different from convective, because convective is based on velocity changing with respect to position, but local acceleration is velocity changing over time. So here's a picture that shows the effect of unsteady flow. Flow that's going under a road through a culvert at time 0, and then later on, after the culvert's completely collapsed, then the flow is different. You know, the flow conditions at the two times are definitely not the same. Let's take a look at another video that just kind of illustrates unsteady flow. All right. We can further classify the flow through channels into whether the channel is prismatic, which means that you have a constant cross-section with regular boundaries, and it could be mirrored along the center line. The channel profile is regular, and if we look from the top, it's straight. But a non-prismatic channel, which is more common in nature, is going to have a cross-section that is variable with maybe floodplains and deltas. It will have a slope that isn't even. It'll have pools in the slope. It'll have certain sections that are really steep and rapids. And then if we look down from above, the flow is setting itself up in a sinusoidal, kind of irregular flow pattern, and it's not going to be straight and narrow under normal circumstances. It's going to find the lowest point in the land, and the flow will go through that. And so that's a non-prismatic channel. In your book, there's a table, table 10.1, that has the geometric parameters of area, wetted perimeter, hydraulic radius, top width, and a parameter called hydraulic depth for a huge variety of different channel shapes. And what we'll see most commonly will be rectangular channels, trapezoidal channels, and the reason that we'll see a lot of trapezoidal channels is that the side slopes for an earth embankment makes it so that we can't have a vertical face on soil. The soil would collapse into an earth-lined channel, and so it's common to have a trapezoidal channel, whether it's just bare earth or if it is grass-lined. You'd really only see a rectangular channel for short segments of concrete or maybe a rock-lined channel. Circular channels are common when we talk about sewers or when we talk about storm drains. They're circular, and it's considered open channel flow because sewers and storm drains don't typically flow full. Normally there will be water in part of the pipe, and the rest of the pipe is open to the atmosphere. And so even though it's flow through a pipe, it's not pressurized flow through a pipe. So we treat it as though it's open channel flow. In your homework, there is a problem having to do with a parabolic section, and I wanted to point out that this table gives you the parameters that you need to, if you have the top width of a parabolic section, and if you know the depth of flow for a parabolic section, then the formula allows you to find the area, wetted perimeter, hydraulic radius, and so on. So these are kind of the geometric parameters that a lot of the formulas we have that estimate the flow rate through that channel, it uses some of these geometric parameters. So you'll find yourself referring to these pretty often as input to other equations. Do you remember laminar versus turbulent flow? What is the parameter that distinguishes whether flow is laminar or turbulent?
If it's above 2,000.
Almost there. 2,000 is the cutoff point for laminar, but what's 2,000 is what?
Reynolds number.
Reynolds number. Very good. That's right. So if the Reynolds number is under 2,000, we have laminar flow. If it's above 4,000, it's turbulent flow, and in between is transition. So within turbulent flow, we can further break it up into 3 divisions. So let's say that we have an open channel and water is flowing downstream. These blue arrows indicate the direction of flow. What we know is that due to the no-slip condition, and because there's frictional resistance at the bottom of the stream, the velocity will be lowest at the bottom and the velocity will be highest at the top because it's in contact with air at the top, and air doesn't resist the movement of a river as much as at the bottom where it's in contact with the soil. So this curve is a velocity profile that's just saying at the bottom of the river the velocity is relatively slow. Well, because of that, there's going to be a zone where the flow conditions are laminar. Where the velocity is low, the conditions are laminar. And remember that the equation for Reynolds number is velocity times diameter divided by kinematic viscosity. And if it's flow through a pipe, it's diameter. If it's open channel flow, it could be, remember we have the 4 times the hydraulic radius substitution that we talked about for non-circular channels. But the point is that when you have a low velocity, you're going to have a layer of a laminar zone. Even though above it the flow conditions are fast and there's a high velocity and you have turbulence above it, there's going to be this cushion of water. It's a thin layer of laminar flow. Well, there's going to be roughness elements. You know, no surface is perfectly smooth. Whether it's concrete, asphalt, soil, sand, whatever the case may be, there's going to be roughness to that material. And the question is, how does the height of those roughness elements compare to the thickness of the laminar zone? If the laminar zone is thicker than the roughness heights, that's what we call smooth turbulent flow. There's transition turbulent flow when the height of those roughness elements is equal to the thickness of the laminar layer. And then rough turbulent flow is when these roughness elements are taller than the thickness of the laminar layer. And so if you have really fast moving velocities, there's going to be a thin laminar layer. And so if you have particularly rough surfaces or high velocities, then you'd expect to see rough turbulent flow. So today we're talking about all the different ways to classify flow, whether it's laminar turbulent or whether it's uniform non-uniform, steady unsteady. Well, even within turbulent flow, there are subdivisions of smooth, transition, and rough. Does anybody have any questions about these subcategories? All right, let's look at the forces of a certain amount of water that's flowing downhill. And so what we have in this figure is the water surface, this triangle and the little lines underneath it. That has a specific technical meaning. What it means is that this water is in contact with the atmosphere. So that triangle means that we can assume the pressure is 0 at the interface of the air and the water. And so as we go down deeper in the water, the pressure is increasing. And this part of the figure is showing that we have a hydrostatic pressure distribution, that the deeper you get in the water, the pressure is increasing. Now, this isn't static water. This water's flowing. And so the pressure isn't described only by the hydrostatic equation, but there still is a hydrostatic effect, where the deeper you go into the water, the higher the pressure is. The depth is getting less. Do you notice how it's deeper upstream and downstream the depth of the water is less? That might be that this water is approaching some sort of a fall. And a waterfall draws down the water in the direction of flow. So there's a curve in this water surface profile. So it's deeper upstream, it's shallower downstream, and so that means here at segment 2, there's not going to be as much pressure because it's not as deep. So those are the first two forces that we could look at. You know, the hydrostatic pressure acting over an area, the area being the height and then the width of the channel, gives us a hydrostatic force from the left, a hydrostatic force from the right. The other two forces are the weight of the water. And so here, gamma, or the unit weight of the water, multiplied by A, which is the bottom cross-sectional area. Actually, I guess A here is where it's the area that we're looking at, because then delta X is what turns it into a volume. And so it's the volume of this water segment multiplied by the unit weight. And so the weight of the water is acting down, and then the final part of the force balance is this shear force that's opposing the direction of flow. So if the water is flowing downhill, the shear force is acting in the opposite direction, and so it's the shear stress multiplied by the area over which it's applied. And so P would give us the depth into the page. Delta X is the distance between the 2 points, and so that describes the area, the bottom surface area of the river, and multiplied by the shear stress gives us a shear force. And so we could do a force balance of this, and that's going to be one part of the governing equations in open channel flow, is using the momentum equation and the force balance that arises from applying the momentum equation, looking at the difference between the momentum on the left side of this control volume, the momentum on the right side of the control volume, and it's from the momentum equation that we can describe the velocity in terms of the friction factor. And so here this F value in the Darcy-Weisbach expression is what we use to estimate the effect of shear stress. So remember, resistance to flow is an important part of understanding what the depth is going to be. And we're predicting depth in open channel rather than looking at pressure. The other element of the governing equations is continuity, so flow in versus flow out. So combining these two ideas together is where most of what we do in problem solving comes from. There's three different slopes for us to keep track of in open channel flow. S sub F is the slope of the energy grade line. And you may remember that in pipe flow, energy grade line was the hydraulic grade line plus the velocity head. So EGL is the pressure head plus the elevation head plus the velocity head. That's EGL. And so in open channel flow, the EGL is this imaginary line that's above the water surface. And how high it is above the water surface depends on the velocity head. The S sub W, the slope of the water surface, is actually asking the question, at a given point, what's the curvature of the water surface itself? And so it's not the slope of the imaginary line above the water surface, that's the EGL. The slope of the water surface is something that we occasionally have to keep track of. And then the other slope is the slope of the bottom of the channel. And so those three things sometimes can be parallel. Those three slopes, if they are parallel, that tells us that we have steady, uniform flow. But if those three slopes aren't parallel, and if the flow is decreasing in depth, then that's an indication that we have non-uniform flow or unsteady flow conditions. So we'll be talking about three different slopes this semester in the open channel. And again, just to emphasize, EGL, energy grade line, in open channel is going to be the depth of the water plus the velocity head, whereas the hydraulic grade line is just the depth of the water. The energy equation looks a little bit different in open channel flow than it did when we were talking about flow through pipes. So far this semester, this is what the energy equation looked like. We had a pump head term. We had head losses, which collectively included both friction losses and local losses. At location 1 in a pipe, there would be the pressure head, velocity head, elevation head. So if the pipe is open to the atmosphere, then we don't keep track of the pressure anymore. In open channel flow, the energy equation changes. So here are the three terms that are in the energy. It's the depth of flow, the velocity head, and then the elevation above some datum. So Z1 means roughly the same thing that it means in pipe flow. It's just the elevation above some basis for measuring all of our elevations. Velocity head means roughly the same thing that it did before. But you'll notice instead of pressure head, we just have the depth of flow, Y1. There's no more pump term in the energy equation with open channel flow. We can't pump water if it's open to the atmosphere. But there are still losses. So H sub F is the losses that are due to resistance. no pumps, and local losses do exist, but we account for them in a different way that we'll talk about in the future. Okay, so the continuity equation, the momentum equation, and we could use the Darcy-Weisbach equation in open channel flow, but it turns out that there's an even simpler approach that's pretty accurate. The Manning equation has a fixed roughness value. This N value is similar to how in the Hazen-Williams equation there's just a single C value that applies regardless of the flow conditions. So the same thing is true when we apply the Manning's equation, that there would be an N value that's just characteristic of whatever material you've got, and then you don't have to change the N value for flow. And it works well for open channel. Manning's equation doesn't work great in closed conduit flow, but we will use Manning equation for open channel. So these are the equations that we use quite a lot. Now, we could further distill the energy equation down to saying it's the total head at location 1 is the total head at location 2 plus the losses that occur between 1 and 2. Now, location 1 has a convention. What we mean is upstream, and 2 is downstream. So flow does continue to have a direction behind it where the flow is coming from 1 towards 2. And the reason for that is that the losses are on the right side of the equation, so they have to be the losses that exist between 1 and 2. Okay, so here's an example for us just to play around with the idea of energy. So what this example is saying is that we know at location 1 the elevation, so the Z term, is 0.782 meters above the datum. And we know the width of the bed, so the cross-sectional view tells us that this rectangular channel has a width of 0.5 meters. And we know the velocity is 0.55 meters per second. And we know E, the total energy. So what that's going to allow us to do is to solve for the unknown water depth, Y. So we'll solve for the water depth, and then once we know the water depth, we can find the flow rate, because Q equals V times A. So we're given E, we're given the velocity, we're given the elevation above a datum. We want to solve for the depth, Y. So rearranging this energy equation to solve for the unknown flow depth and substituting in the given energy, the known velocity information, the elevation above the datum. So the flow depth should be 0.654 meters. And then if we know the velocity, we can calculate the cross-sectional area because it's the half-meter width multiplied by the depth that we just calculated. So the depth is 0.654, the width is 0.5. So that's going to give us the cross-sectional area. So the flow rate should be 0.18 cubic meters per second. So the homework assignment you've got due on Wednesday, it's like kid stuff like this. Pretty easy. Just like little puzzles. So mostly. I mean, there might be a hard one in there, but it's mostly just, well, if the width is that and it's a rectangular channel. All right. So this E is called specific energy. And we're wanting to find what's the energy at a given location above the datum. If we have an inclined channel, we will usually make a simplification that I want to talk about. And that is, there's going to be a small angle if it's an inclined channel here. And the length of the channel segment is going to be less than the plan view length if we're looking down from above. So you'll notice here this is going to be, it's longer. So L, the hypotenuse of that triangle, is longer than the top view that we would measure on a map. And so sometimes people are wondering, is it okay to just use the length of a river that you're measuring from an aerial photo, or do you need to correct for what's the physical length of that river, accounting for the angle and the slope that sets up? And the way it ends up is that as long as the slope is less than 10%, then the cosine of the angle is going to be so close to 1. Even for a slope of 10%, the cosine of theta is going to be about 99%. And so the length and the length times cosine theta are about the same. So in open channel hydraulics, we usually won't distinguish between whether we're talking about the physical length of the channel or the top view length that's measured on a map. But down is considered positive for a slope. So when I say like a river is on a 1% slope, I don't mean that the river is going uphill at 1%. It's just taken as a given that we're talking about a negative slope is described in positive terms. So we don't bother putting the minus sign when we talk about the slope of streams or sewers. It's assumed. And so you can calculate that slope by the upstream elevation minus the downstream elevation. And if you like, you can divide by the length times cosine of theta, but usually theta is so small that you don't need to include the angle in the denominator. Just the length itself will be sufficient. One of your problems asks about flow regime. So you've already seen Reynolds number, which is laminar versus turbulent flow. Another way to classify flow is whether it's supercritical or subcritical. We're going to go into a lot of stuff about supercritical and subcritical, but it's calculated with a Froude number. And it's similar to just how, there is a threshold that above which is turbulent flow, below which is laminar. So that's 2,000 and 4,000. The threshold for the Froude number is 1. And if the flow is greater than 1, then the regime is supercritical. If the Froude number is less than 1, then the flow regime is subcritical. So on that homework assignment where it asks you to classify the flow regime, what I'm asking you to do is calculate the Froude number. And so you'll need to know the velocity of the flow, and then in the denominator, g is just the gravitational constant, but then this y sub h is a parameter that includes the cross-sectional area of the channel and the top width. So there are several different equations for Froude number. This is one of them. I'll show you more later, but I think that this is all that you'll need in order to classify the flow regime for that one problem. So we'll work this example when we get together on Monday, but for now I will just close with one last look at the announcements that the assignment's due on Wednesday, so you should get an early start over the weekend on some of those problems, and I will see you on Monday.